Our journey to the Orbital City begins in 2028. This video maps the realistic future timeline for building the first permanent space colony. The entire project hinges on one device, the Mass Driver.
2028, Artemis III and the resource shift. The year 2028 marks the end of an era. NASA's Artemis III mission, using its powerful Starship human landing system, achieved its primary objective. But the scientific triumph wasn't just the footprints left on the lunar South Pole. It was the confirmation of vast, easily accessible deposits of water ice locked away in the shadowed craters. This water wasn't just for science. Through electrolysis, it yielded pure hydrogen and oxygen, the most critical propellants imaginable. The Moon, almost overnight, ceased being just an object of exploration. It was instantly redesignated as the solar system's most critical logistics depot. The global focus shifted from merely visiting space to finally utilizing it. 2035. The Great Retirement and Commercial Succession. The change continued in low Earth orbit. The venerable International Space Station, a marvel of international cooperation, had reached its operational limit. True to plan, by the end of 2035, it was formally retired and safely deorbited into the Pacific's oceanic graveyard, Point Nemo. But low Earth orbit didn't stay empty. Its role was swiftly taken over by a new fleet of competing, privately owned commercial platforms. Companies like Axiom Space, Starlab, and the rapidly emerging Indian Bhartiya Antariksha Station modules began operations. They weren't research labs, they were orbital workshops. They proved beyond a doubt that microgravity created technically superior products. Flawlessly clear fiber optics, perfectly structured bioprinted organs, and high-purity semiconductors. The quality problem was solved, but the crippling cost of launching raw materials from Earth meant the entire industry remained unstable, financially trapped in a cycle of high-risk investment. 2045. The commercial viability pivot. The Indian breakthrough. By 2045, the promise of the orbital economy was faltering. Low Earth orbit factories, despite their innovative products, were bleeding money. The launch tax on Earth-sourced raw materials was simply too high. The dream was about to die. The solution came not from the established aerospace giants, but from a surprising quarter: the rapidly expanding Indian space sector. Agni Labs perfected a highly efficient, high-speed orbital-to-orbital cargo transfer system. Using advanced electric propeller tugs, they created a steady, cost-effective pipeline from the Moon's L2 point, a gravitational sweet spot perfect for staging, directly to the low Earth orbit factories. It was more than just a rocket. It was a logistics breakthrough. The cost of resupplying those orbital workshops with Moon-derived propellants and feedstock plummeted by 60%. Suddenly, superior microgravity products became affordable for terrestrial mass markets. Billions of dollars flooded into orbital infrastructure. The industry achieved true commercial viability, setting the stage for projects far grander than anyone had imagined. 2056. Radiation solved and the asteroid pipeline. With profitability secured, attention turned to making orbital space truly habitable long-term. By 2056, scientists deployed permanent, automated radiation monitoring and mitigation systems. Using a thick, self-healing slurry derived from lunar regolith, they built effective biological shielding around key orbital assets, finally solving the critical health risk for long-duration habitation. In parallel, initial automated missions to near-Earth asteroids proved tantalizing. These weren't barren rocks, they were floating treasure chests of valuable metals. While still a developing industry, the first large quantities of asteroid-sourced metals began trickling into the Earth-Moon system, hinting at an even grander supply chain. 2058. The Mass Driver. The final economic barrier fell in 2058. A Western-led consortium, the Interloon Corporation, deployed the first fully operational, automated mass driver on the lunar far side. Imagine an electromagnetic railgun, kilometers long, permanently anchored to the lunar surface. It takes refined lunar regolith, silicon, aluminum, vital shielding material, packs it into small, uniform capsules, and accelerates them using only electromagnetic force, no chemical fuel. It launches these packets, one after another, at immense velocity, aiming for the L2 assembly zone. This was the pivotal moment. The cost of transferring bulk construction materials into space dropped to fractions of $1 per kilogram. Building structures weighing millions of tons was no longer science fiction. It was an economically viable construction project. The age of the megastructure had arrived. 2070. The Great Assembly Project. With materials abundant and cheap, the engineering focus snapped to Earth orbit. Orbital Engineering Collective, a mega-consortium spanning dozens of nations and corporations, was founded with a single, colossal task: Phase 1 construction of the largest ever orbital structure, a rotating Stanford Torus design. In 2070, utilizing the flood of asteroid-sourced metals and lunar regolith composites, assembly began. The structure wasn't designed for luxury or tourism yet. It was initially a vast orbital shipyard and testing platform, a skeletal frame to test automated construction techniques, in-space 3D printing with extraterrestrial resources, and, most critically, the physics of artificial gravity. This structure was being built for function, out of sheer necessity. 2080, achieving 1G for the first time. The first and most vital challenge was biology. Prolonged microgravity is a subtle killer. Bone loss, muscle atrophy, and damage to the optic nerve. Humans were simply not built for it. The theoretical solution, known for decades, was rotation. The massive torus, now nearing its final 1.8-kilometer diameter, needed to spin just fast enough to create the outward push, the centripetal acceleration that mimics Earth's pull. In 2080, the engineers achieved the impossible. They successfully spun up a significant prototype module within the main structure to a rotation rate that generated a sustained 1G of artificial gravity. This was more than a technical achievement. It was a biological declaration of independence. The rotation rate was agonizingly slow, less than 2 rotations per minute, to prevent inner ear disturbances. The health barrier to permanent human settlement was cleared. The Orbital City was now viable, not just as a workplace, but as a healthy, permanent home. Public announcements for orbital residency applications began immediately, triggering a space real estate rush. 2105. The internal ecosystem closure. A home isn't just a place with gravity, it's air, water, and food. A city of 10,000 people cannot rely on Earth resupply. The logistics would still be crippling. New Tranquility needed to become a miniature, self-contained Earth. This challenge fell to the bioengineers. In 2105, the primary residential ring, dubbed the Astrodome, achieved closed-loop ecological closure. This meant the entire system, air, water, and over 80% of food, was constantly recycled and regenerated internally. Water recovery systems purified every drop of wastewater and perspiration to near-perfect efficiency. Air revitalization units, supported by massive vertical farms, scrubbed carbon dioxide while producing oxygen and the bulk of the city's sustenance. The orbital city was now truly resilient. It could survive indefinitely without critical support from Earth or the Moon. The first wave of permanent residents, families, artists, and entrepreneurs, not just engineers and miners, moved in, establishing the first true off-world independent human culture. The island in space was ready. 2115, grand opening of New Tranquility and the next race. In 2115, the OEC, having completed its final internal outfitting, rebranded itself as the New Horizons Trust and unveiled its completed megastructure, New Tranquility. It stood as the ultimate expression of human ambition, capable of housing over 10,000 residents, boasting zero-G sports arenas in its central hub, and offering breathtaking panoramic views of Earth. For a brief, shining moment, humanity was united in the awe of what it had built. We had broken the chains of gravity and achieved our high frontier. But this triumph wasn't the final chapter. It was the end of the prologue. Because where one frontier opens, a new competition immediately begins. Even as celebrations echoed through New Tranquility's rings, reports from the far side of the planet showed the rival Tianqing Industries accelerating construction on their own, even larger orbital structure. Their focus, not just habitation, but critical energy production via massive, efficient, space-based solar power arrays. The age of orbital cities had truly begun. We built the first home in the high frontier to escape the limits of Earth. But in the next century, we would learn that humanity simply took its greatest competitions with it.